Okay, so good afternoon from Helsinki and welcome to this UNU-WIDER online seminar. My name is Simone Schotte and I'm a research associate here at UNU-WIDER. And yeah, I'm very happy to see that we have a really big audience today. So this is really great. And for those of you who are joining us for the first time, so UNU-WIDER stands for United Nations University, World Institute for Development Economics Research. And at WIDER, we undertake research and policy analyses, focusing particularly on the most pressing concerns affecting the living conditions of the world's poorest. We also aim to provide a forum for knowledge exchange, discussion, and debate between researchers and development professionals, and on those issues, and offer capacity building and training for researchers and decision makers in economics and social development. So I'm extremely excited and pleased to be joined today by a very distinguished speaker, Pedro Sant'Anna, who is a senior research economist in the Office of the Chief Economist at Microsoft Research, and also an assistant professor in the Department of Economics at Vanderbilt University. Professor Sant'Anna is an econometrician who mainly focuses on the area of microeconometrics, with a particular focus on program evaluation and causal inference. And together with Bradley Callaway, he's the author of what in my view is one of the most exciting papers in econometrics that I have had the pleasure to read over the past year or so. And their paper on difference and differences of multiple time periods, which he's going to present to us today, came out in the Journal of Econometrics in December 2020. Actually, both the speaker and the topic of the seminar are a bit extraordinary for us, considering that our usual wider seminars tend to be a bit less technical and methodology focused and feature more applied research. However, and I think seeing so many of you in the audience today really confirms this paper has clearly sparked a lot of interest among applied researchers, as it is offering a modeling approach that can be used in situations that many researchers will face when studying policy. And this is a type of situation when units select into treatment at different points in time. And Goodman-Bacon 2019 has shown that the two-way fixed effects estimator, so panel fixed effect with time dummies, is going to be biased in these situations if we have a rollout of a policy and heterogeneous treatment effects over time across those different cohorts. And I'm sure that many of you in the audience have themselves maybe conducted difference and difference analyses, potentially even involving this type of setting, and are now eager to learn about the type of solutions that are available to avoid this sort of bias and transparently estimate the effects in the setting. So really excited about this. And before I turn the microphone over to Pedro, just a few words on how the seminar is going to work today. So we will first listen to Pedro's presentation and then should have a good amount of time for a Q&A session together. So for this, you can submit your questions using the chat function throughout the presentation, and then I will administer your questions to Pedro at the end of his presentation. For this, at that point, we will allow you to unmute yourselves and ask your questions live, but we will keep you muted during the presentation. And I apologize in advance if we may not get to everybody's questions, as we are a rather big group today. So just as a final remark, this seminar is being live streamed to YouTube and is also being recorded, and the recording will be shared on our webpage and on the wider YouTube channel afterwards. So let me now turn over to Pedro. Welcome. Really excited to have you here, and the floor is yours. Thank you.
Thank you very much, Simone, for the very nice introduction and like very generous introduction as well. It's a very great pleasure for me to have all of you here listening to like one of my recent research, recent paper in my research agenda. And as Simone was mentioning, this is joint work with Bradley Callaway, which is a good friend and somebody that I had the great pleasure to work with. Yes. And I mean, I have learned so much from Brent, right, that I cannot put it in words. So I'm going to try to give it back to everybody, like everything that I have learned from him in this presentation. So long story short, like Callaway and Sant'Anna, like in practice. So I'm going to talk a lot about different tools, different techniques, but I want to make sure that like in practice, everything that I'm going to be talking today can be easily implemented in a couple of lines of code, right? So all the proposed tools that I'm going to be mentioning today can be easily implemented when you have access to panel data or repeated cross-section data. And we have an R package, DID, which makes this usage relatively simple, right? We also have some Stata wrapper available, and we are also working on a native Stata implementation that's hopefully going to be out in the next months, like by end of August. Hopefully everything's going to be good to go, right? So, but what is the fuss about difference and differences, right? So what everybody's talking about, so what is the empirical relevance of Callaway and Sant'Anna? So to answer this question, right, there is this very nice paper by Curry, Cloven, and Zewers in the AAPNP 2020. And what they did is like they did a kind of machine learning search for the frequency of several keywords, how often those keywords appear in the NBER working papers and on top 5 journals in economics. So from this plot, it's very clear to see like that as time went on, the popularity of difference and differences, regression discontinuity, event study, and bunching is like clearly increasing over time. But what I want to call your attention is not about the trend, but it's about the level, right? So if you open up, if you take a look here on NBER working papers, like among all empirical working papers in the NBER around by 2017, around 22, 23% of them mention the word difference and difference. And just for a matter of comparison, we all know that regression discontinuity is also very popular, right? It's also very commonly used tool in economic setups, in policy evaluation. I mean, but that's 10% around 2017. So difference and difference is twice as popular using this metric, right, than regression discontinuity. So essentially, what's the empirical relevance of Callaway and Sant'Anna? Well, difference and differences. It's everywhere. It's arguably the bread and butter of empirical research in social sciences, right? But before talking about this paper per se, it's worth it to go back and like digress a little bit about the canonical setup, like what everybody already knows about difference and differences. So in the classical setup, we have two groups, right? So group G equals to 0 and group G equals to 1. Group G equals to 0 is never subject to the treatment. Group G equals to 1 is subject to the treatment in time period 1, right? So we have also 2 time periods. So 2 groups, 2 time periods. I'm going to refer to this as the 2x2 DID. In this canonical setup, we know that the parameter of interest, right, underlying difference and difference methods is the average treatment effect on the treated, which is just like what is going to be the average treatment effect among units who are actually treated, right? And I want to see this effect at time period 1. The first component of this ATT here, whatever is in black on the right-hand side, we know that that's recoverable from the data, right? Because we observe Y1 among treated units in time period 1. However, the blue component here, it is the potential outcome in the absence of treatment in time period 1 among units who actually receive the treatment. This blue component, no matter how much data you have, right, you're never going to be able to recover it without extra assumptions. So that's the canonical problem of missing data, right? So causal inference is hard because no matter how much data you have, this blue component, I mean, data by itself cannot help you to recover it. So what's the name of the game we're going to be playing? Well, if you cannot recover from the data only, we're going to make some extra assumptions to be able to recover it. And the key assumption in difference and difference setup, it is the so-called parallel trend assumption, right? In this 2 periods, 2 groups case, it just tells that like in the absence of treatment, the evolution of the outcome among units who are actually treated would evolve, will be the same as the average evolution of the outcome in the absence of treatment among units who do not experience treatment. Once I have this setup clear, right, we are actually able to recover the ATT, right? And we can implement difference and difference in 2 different ways. The first way is that I would say like is the ATT hat n, which is a simple comparison of mean. I refer to this as like difference and difference by brute force because we actually manipulate things, we do things like by comparison of means by hand. But in practice, very often researchers do not do DID by brute force or by hand. What we usually do is we rely on a regression specification that is in this 2x2 setup. It is recovering the same parameter as in the brute force DID. So this regression specification is going to be like, well, I'm going to regress the outcome Y on a constant, a group dummy, a post-treatment dummy, and the interaction between post-treatment and group dummy. And this beta on this two-way fixed effect specification, right? We can show that like under parallel trends and non-anticipation assumption, it is equal to the ATT. We as economists, we really enjoy seeing things work in a regression because we are kind of regression addicted, right? So we understand regressions well. And once we see these things, oh, I can do the idea in a regression. So we can leverage all our knowledge of how to do inference, on how to do specification testing, how to do falsification testing, clustering, and many different setups once we see things in regression. So we like regressions because of that, at least in my point of view. But what happens? At the universe of difference and difference paper that I mentioned a couple of minutes ago, right? They don't necessarily fit into this canonical 2x2 setup. How so? Many times researchers are going to use covariates to kind of say, well, I want to adjust for covariate specific trends. They're going to put covariates into the regression. Furthermore, it's very often like we're going to have more than 2 time periods. And once you have more than 2 time periods, right, instead of having T pre and T post, I'm going to have T equals to 1, 2, 3, 4, 5, up to 10 or 20 or capital T in general. Once we are in this world with many time periods, we have somehow to entertain the possibility that not everybody is subject to the treatment in the same point in time. So for instance, I may be treated today, right? But Simone may be treated in 10 days from now, and Brent may be treated like in 20 days from now, and so on and so forth. So once we have these very many time periods, we should somehow entertain the possibility of having variation treatment timing. And once we do this, well, we are not in the canonical setup anymore. And here comes the key. So once we are like, well, we see that everything worked somehow well in the 2x2 setup. So in this with many time periods and variation treatment timing, it's very tempting for us to extrapolate from the canonical setup and rely on a quote unquote generalization of that specification before. So how does that generalization work? I'm going to regress the outcome YIT, right? Instead of having a group dummy, I'm going to have a unit fixed effect. Instead of having a post-treatment dummy, I'm going to have a time fixed effect, right? And instead of having the interaction between post and group, I'm going to have a bunch of leading and lags of treatment indicators, right? So this DITK here, it is just us asking the question to unit I at time period T, if this unit has been treated by K periods. Right? So when K is equals to 0, and this dummy is going to be equals to 1 if unit I is in its first period that is experienced the treatment. DITK equals to 1 is going to take value 1 if I am 1 period after treatment has taken place. DITK equals to 2 is going to be equals to 1 2 periods after treatment has started, and so on and so forth. Right? So this is the specification you're going to have. And here, this gamma K lags is arguably supposed to capture treatment effect dynamics in event time, right? So gamma K lag is supposed to capture how treatment evolves over time once treatment has taken place. Likewise, gamma K lead is supposed to capture like potential violations of parallel trends and potential violations of non-anticipation assumption, right? So in an ideal scenario, all gamma K leads should be equals to 0, right? If this is actually recovering what it's supposed to recover, and gamma K lags going to reflect treatment effect dynamics. So so if everything worked in the 2x2 case, right? And this is kind of like generalization to the multiple periods, multiple groups case, this should work as well. And this has been the mentality for many, many years. So to illustrate the potential dangers of extrapolating from something that we know it works to something that we hope it works, let's consider a very stylized example. right? So I have here like 4 different groups. So group red is first treated in 1986. Group blue is first treated in 1992. Group green is first treated in 1998. And group purple is first treated in 2004. And if I look at this graph, I say, this is great. Everything looks so parallel, right? So before treatment takes place, everything is like moving like together. We have everything is like treatment effect seems to be big, right? So what we're gonna do? Let's look at this data set, this example, and we're gonna generate this data like many times, and I'm gonna estimate this specification here, like in each point, in each simulation draw, and I wanna see how gamma K lead and gamma K lag, like how it represents, what is gonna be spit out of this procedure. Right, so here I have more details about the specification of how I generate this data. These slides are also available on my webpage, so you can see things there. I also have like details of this simulated exercise on a kind of blog post on my webpage, so you can go and play around with this as well. But for the sake of time, I'm gonna go a little bit faster on the details with this. So what I'm gonna do, generate data that respects all the assumptions that I can hope for, estimate gamma K leads, gamma K lags. I'm gonna focus on K and L equals to 5. So I'm gonna look for a time window from 5 periods before treatment takes place to 5 periods after treatment takes place. And everything that is outside is -5 and 5, I'm gonna bin the endpoints. Once we do this, the red line here is what's supposed to be the true treatment effect dynamics. So there is no pre-trends, everything is good, and treatment effect is growing over time. What I have here in blue is what is coming out of this two-way fixed effect specification, right? What is striking here, at least to me, is that if I display this result, the blue lines for you as an empirical researcher, you're going to look at this and say, yeah, you know what? I don't believe on this design because we have pre-trends, right? I don't believe in this design because we have violation. It's not arguably there is some violation of the parallel trend assumption. But what's should emphasize here is that, like, well, the design is perfect, right? That is the red line, there is no pre-trends, treatment effect dynamic is growing, but the estimation method we are using, it's messing things up. But then what happens? I have bin the endpoints here, the -5 to 5. What happens if I don't bin? I include all possible leads and all possible lags, right? Bias are still there, right? So these two-way fixed effects going to still be potentially problematic. So me as an econometrician, I see this plot say, great news. I have room for improvement. I can work on this topic. I can do something that is better, right? And that's more or less the birth of Callaway and Sant'Anna, right? So our paper comes and say, well, if you are in these setups when you have variation treatment timing, right? You have multiple time periods and you want to construct a difference procedure that respects your assumptions, right? This is our paper, what do we do? And once we do this, we can hit the red line perfectly. Right, so the Callaway and Sant'Anna is all, this is essentially the setup. We're not gonna restrict treatment effect dynamics. We're not gonna restrict treatment effect heterogeneity beyond the implied assumptions by the implied restrictions by the parallel trend assumptions. And once we do this, we're gonna be able to fit perfect, like kind of like quote unquote, perfect event study plots like this. I have to stress, right, for the sake of transparency and honesty, that of course, we are not the only paper out there that is proposing some of these tools. In fact, we have witnessed a big boom of difference and difference methods in the last 5 years or so. So here I'm only mentioning the papers that were more or less simultaneous, came out more or less the same time as Callaway and Sant'Anna. After, I mean, there are many additional papers that should be added to this slide, but I haven't updated my slides for a while, so it is what it is. So I want to stress here, like in this kind of mini DID revolution, there are papers such as Afi and Ibens, Borussiak and Jaravel. By the way, they have a new version, it should be Borussiak, Jaravel, and Spies now. Deschamps Martin and Dalton Fourier, Goodman Bacon, Salan Abraham. These papers also touches on several of the issues that Callaway and Sant'Anna touches. Perhaps mostly important, all these papers have results that we do not have, right? So Callaway and Sant'Anna has nothing to do with the problems of two-way fixed effects. Right? So these slides that I have shown you, all the bias of event study dynamics and two-way fixed effects estimation procedures, Callaway and Sant'Anna do not explain why they appear, right? Why it's there. All these other papers have explain the variations of that specification that I have included and explain the problems. Among those, the one I would like to call your attention for is Sun and Abraham. So this Sun and Abraham is a very nice paper that came out in June of Econometrics at 1 or 2 weeks together with ours. And they explain the sources of the bias of the event study specification that I have shown you in a minute. Right, so these papers have results we don't have. On the other hand, Callaway and Sant'Anna has, I would like to say that like we have some unique features in our paper that make it also very attractive compared to others. So to kind of help you to navigate this literature without going too much into the details, some things that I believe that is unique to our procedure is that we're gonna allow covariates to enter this difference and difference specification in a flexible form. When I say flexible form is like, well, we're gonna assume that parallel trends holds conditioning on covariates. And once we allow for that possibility, it's kind of opening a Pandora box, right? Because now I have different estimation procedures that I can use, right? And still deliver the same target parameters. So in the paper, we discussed how we can use regression adjustments, inverse probability weighting, or double robust procedures to estimate ATTs, event studies, and other aggregations, right? So also what's unique to Callaway and Sant'Anna, I would say is the mentality, right? Is the procedure of clearly separating the analysis into 3 steps. We're gonna have an identification step, we're gonna have an aggregation step, and we're gonna have an estimation and inference step, right? About the aggregation step, what we stress a lot in our paper is that it's very hard to talk about quote unquote the causal effect, right? Because they have different target parameters. So I can aggregate our causal effects in different ways that's going to lead to different target parameters. So in the paper, we also discuss several of these aggregation schemes that can be used to highlight heterogeneity in different dimensions. Also, we talk about panel data and stationary repeated cross sections, and we try to relax as much as we can the assumptions about the underlying assumptions behind difference and difference and event study procedures. So this is more or less like the way I navigate. But without further ado, right, I would like to jump in and explain the main building blocks, right? So in other words, how does Callaway and Sant'Anna work in the sense that like, how can I get those kind of good looking event study plots? To do that, I'm gonna have to introduce notation, and I'm gonna focus in the presentation to the case when I have a balanced panel data, right? So I have T time T, like I have Y1, Y2 up to YT. I have these treatment dummies, D1, D2, DT, and I have a vector of time invariant covariates Xi, right? So DI here, DIT takes value 1 if unit I is treated in period T and 0 otherwise, right? So this is essentially, if I am treated by that period, I'm going to have DI equals to 1, DIT equals to 1. If I am not treated by the time, I'm going to have DIT equals to 0. We're also going to introduce a new notation, new terminology, which are cohort dummies or group dummies, the way we call it, which is like GI little g. GI little g takes value 1 if unit I is first treated at time g. So everybody who shares the same starting day of treatment has the same, it belongs to the same group. So the definition of group that we have is like, well, everybody is depending on the starting date of your treatment. So everybody who starts treatment on a given day belongs to the same cohort, the same group. Because a group that never experienced treatment in this time window is kind of special for us, we're gonna like allocate a different notation for the never treated units. So C equals to 1. So C is gonna be a dummy variable or an indicator that takes value 1 if this unit never experienced treatment in this given window. Right? So we're going to allow for units never being treated in the time window but this is not a requirement, right? So if you do not have if everybody is eventually treated in the time frame, this is still okay, good to go. The last thing that I want to stress in this slide that Callaway and Sant'Anna, it's all about staggered treatment adoption. And this means that, like, well, once I am treated, I am forever treated, right? So this means that I do not forget my treatment. So even if treatment turn off later on in the future, right, I'm going to denote here by treatment variables. So the group variables that is going to denote here is going to be the first time you experience treatment. So there are other procedures in the literature, like especially those by Deschamps-Martin and Dalton-Follier, that handles like treatments turning on and off, right? And Callaway and Sant'Anna does not do that because we are in a world that we believe that people do not forget, right? Notations get slightly more complicated in this treatment on and off setup, but I would like to refer to the paper by Clément and Xavier that they talk this more extensively than I have time to explain here. A second assumption now is that, so this is set up now about assumptions, right? And this is very important because these are not innocuous assumptions. The first assumption we're going to make is that a kind of no anticipation assumption. This means that, like, if I believe that nobody anticipates treatment, I'm assuming that before treatment takes place, treatment effects are zero for all cohorts, right? So this is essentially in the notation that I have here with limited treatment anticipation. Take delta equals to zero, right? This is telling that there is no treatment effect before in all pre-treatment time periods. The assumption that we have here is slightly more general because we can allow for treatment anticipation as long as this anticipation is known, right? So if I know, oh, units anticipate treatment by one period. So what do? I kind of like reshift, I redefine treatment to being like, well, treatment date -1. Right? So by playing around with this thing, we can allow for some types of anticipation, but not others. The second assumption here, so this is like delta, if you take delta equals to 0, this is a no anticipation assumption. Delta is strictly greater than 0, is going to be some kind of limited anticipation that is known and homogeneous across units. The last assumption is about overlap condition, right? So this is kind of to avoid extrapolations and to make the inference procedures more standard. So that's more or less where we're standing. So now we have to define what we're after, right? So as I mentioned before, we're going to have variation treatment timing, and we're going to have different groups. So in Callaway and Sant'Anna, the building block of the analysis, it is a parameter that we call the ATT-GT. What is ATT-GT? This is measuring the treatment effect, the average treatment effect among units who belong to cohort G, right? And I want to see the treatment effect of starting treatment time, starting treatment at time little g versus never being treated. So Y0 here is never being treated. And I want to see this effect in calendar time period G, in calendar time period little t. So what I'm going to do is like, well, for those units who are treated for the first time today, what is the treatment effect today? What's the treatment effect tomorrow? What's the treatment effect in 10 days from today? Right? So this is going to be our ATT-GT. So for different cohorts, right, I want to see the evolution of treatment effects over time. And again, I'm zooming in here in only post-treatment periods because for T is strictly less than G minus delta. The no-anticipation assumption implies that ATT-GT is equal to 0 for pre-treatment periods. Once we agree this is the main building block of our analysis, right, we have to say, well, how can we identify this animal from the data, right? Again, among units who are treated, we're never going to be able to observe YT0, so you're going to have to supplement this data work with some important assumptions. And this is, again, now you're going to extend assumptions in terms of what kind of comparison group you're going to use. So in the 2x2 case, we have talked about parallel trends, right? So here we're going to have to talk about parallel trends as well because we are in difference and difference words. But here, they are not one parallel trend. There are potentially very many different parallel trends. So I'm going to talk about two extremes versions of these parallel trends, but there are places in between, right? So you can choose other parallel trends depending on how you construct your comparison group. But let's talk first about, quote unquote, the natural extension of the 2x2 case. It's in a setup when I have a cohort that is never exposed to treatment. And I am comfortable using that cohort, I would say like quote unquote, clean cohort or untreated cohort. I'm okay of using that cohort as a comparison group for all other cohorts. So in that setup, I am willing to impose a conditional parallel trends, right? Such that the evolution of the outcome given covariates among cohort G, it is on average the same as the evolution of the outcomes, right? In the absence of treatment for cohort who is never exposed to treatment given covariate X. So we allow for covariate specific trends, right? And we are using the never treated units as a comparison group for everybody in my data. But you look at me and say, well, what's so special about the never treated units? Why should I use them? Perhaps the never treated units are so different from the eventually treated units, and I don't want to use the never treated units as a comparison group in my application. Or think in other setups, I may not even have a never treated unit in my data. So everybody's eventually treated, so I don't have a never treated group. What can I do? And here comes an alternative, right? So I can, instead of using the never treated as a comparison group, I can use the units who are not exposed to treatment by time t. So all units who have not yet been treated as a comparison group.
Pedro, you have about 10 minutes left for your presentation.
Perfect, yes. So once we agree on these comparison groups, and this is important, right? So you have to decide this a priori on which comparison group you believe is more credible for your own application. Once we are in this setup, like everything is essentially back to the 2x2 case. So let's ignore covariates for the moment. So covariates plays no role, parallel trends holds unconditionally. If I'm willing to use the never treated units as my comparison group, we show that you can identify the cohort-specific average treatment effect on the treated by moving everything back to the 2x2 case. Right? So what I have here in this equation, it is, I'm going to have two groups, right? So cohort G and cohort never treated. So I'm back to the two group case. And I'm also going to have two time periods, time period T, which is post-treatment period, and time period G minus delta minus 1, which is pre-treatment periods. Right? So essentially, what we did here, it's like take this complicated animal, slice the data in a way that respects our assumptions. And once we do that, we are back to the 2x2 case. So we can actually identify this cohort-specific or group-specific or group time-specific average treatment effect. It's very similar to the classical 2x2 case. The only difference that we're going to have to go take long difference. So YT minus Y, G minus delta minus 1, right? So instead of having YT minus 1. So we're going to have to take long difference. And this baseline period here, it is the last time cohort, the last time before cohort G was effectively treated. So if you don't want to use the never treated units as a comparison group, but you want to use the not yet treated as a comparison group, how things differ? Well, this first component is going to be exactly the same. The second component is going to be just a matter of playing with the comparison group. Right? So I want to use all cohorts who have not yet been treated by time t plus delta as my comparison group. And here delta, again, is playing the role of anticipation. So if you believe there is no anticipation, delta is equals to 0. So essentially, everybody who has not yet been treated today, right, can serve as my comparison group, right, for treatment effects today. So everything is very similar. We are back to the 2x2 case because we're going to have two groups, cohort G and cohort not yet treated by time t plus delta. And again, we have two time periods, t, which is post, and G minus delta minus 1, which is pre. So again, we slice the data in a way that our assumptions are fully respected. If you want to allow for covariates, the formulas look a bit more nasty, right? But the intuition is exactly the same. So what I'm displaying here, it is what we call the double robust procedure to recovery the group time ATTs. And this is double robust because we're going to model the probability of belonging to cohort little g, and also going to model the outcome evolution of the never treated units, right? So we're going to model two components of the DGP, but as long as one of these components it is okay, I don't care about the other being wrong. Right? So essentially, we're going to have two shots, right, to hit the ATT. If my propensity score is correctly specified, we are good to go. I don't care about my outcome equation. Likewise, if my outcome equation is correctly specified, so I have a regression model for the outcome evolution of untreated units, if I'm good modeling that perspective of the data, we don't care about propensity score. So we're going to have two shots to hit the same target, right? So this is very attractive because the model is less sensitive to modeling assumptions. So I'm going to fast forward this, right? Because, so up to now, what we did, we talk about ATT-GTs. And you look at me and say, Pedro, you're slicing the data so much, right? You're cutting the data into groups, to time periods. If I have many time periods and many groups, each of these pieces are not informative, right, for me. Or perhaps I have too many of these pieces that I don't know how to display this information for policy analysts or for or for policymakers, or even to display for the scientific community. So the way we want to move forward, it is well, we should think about each of these pieces of the ATT-GTs as a Lego piece, right? And what's the beauty of Lego? Is that we have infinitely many options to build with these pieces. So if each piece, if each ATT-GT is a piece, now what I'm going to do? I'm going to get all these pieces together and construct something that is meaningful to me, to my own application, right? Like Lego, what I may find interesting, Simone may find boring, right? Or what is informative for me may not be informative for Simone. So what we're going to do here, we're going to propose different ways of aggregating these ATT-GTs that are able to highlight heterogeneity in a way that is meaningful for my own application, right? So essentially, we slice the data a lot. Now is the time of gluing the data together, right, to be able to conduct more reliable inference, right? So the way we're going to proceed is well, what kind of aggregation we're going to do? You can think about, well, you pick the weights, right? So I'm going to get every single ATT-GT that I have here. I'm going to look only at post-treatment periods. And for each GT pair, I'm going to assign some weight, these WGTs. So the name of the game we're going to be playing, it is coming up with meaningful and informative weights, WGT, right, that can highlight heterogeneity in my own application. The simplest way of aggregating is to pick in, well, every unit in my data going to have the same weights. So I'm going to get all these ATT-GTs. I'm going to weight them all the same, right? And this is what we call theta M0 here. But then what happens? Some cohorts are big, some cohorts are small, right? So this aggregating all ATT-GTs, regardless of the size of the cohort, it's kind of potentially misleading. So I would say, well, you know what? Bigger cohorts are going to have bigger weight. Smaller cohorts going to have smaller weights. So this is a weighted average, right, which we denote by theta W0. The problem of this strategy, it is that units who are treated early on, right, in the panel, they appear more often in this scheme. So they somehow overweight units that have been treated earlier. So what is the solution? Well, let's come up with different weights that do not suffer from these problems. And perhaps I want to talk about one of these weights, which we believe is to be the most popular weight in the literature, which is related to event study dynamics, right? Which relates to the early plots that I have shown, like in the beginning of the presentation, that highlight how treatment effects evolve depending of how long you are since treatment has started. So here, what we're gonna do? We're gonna first relabel T. So what I care is like, I don't care about calendar time in this aggregation scheme. What I care is about how many periods have passed since treatment has started. This is gonna be denoted by E. So instead of having T, I'm gonna relabel T to be G plus E, right? So E equals to 0 is the instantaneous treatment effect. E equals to 1 is what happens 1 period after treatment has started, and so on and so forth. So once I relabel this, all I'm gonna have to do is like, well, among units who have been exposed to treatment by period E that I have data available, I'm gonna reweight them such that bigger cohorts have more weights than smaller cohorts. So the weight's gonna be proportional to cohort size. Once I do this, I have this theta D E, right? And then this is what we like the procedure that we push forward for the summarizing treatment effects dynamics with respect to event time. There are other aggregation schemes in the paper as well, but I'm out of time, right? So what I would like to go, this is not the only one that you can use. If you want to highlight if treatment effect heterogeneity with respect to cohort, you can take a cohort aggregation. If you care about treatment effect heterogeneity with respect to calendar time, right? So if you see if treatment effect that varies if you're in a boom or a burst period, you can aggregate with respect to calendar time to highlight calendar time heterogeneity. And there are many different schemes that you can do it. So the beauty of Callaway and Sant'Anna, it is to kind of like open this box, right? So for you and letting you choose the weights that is actually meaningful for your own application, right? So in the paper, we also have an empirical application. I'm going to skip that because I'm out of time, right? So just to conclude, the main message of Callaway and Sant'Anna, it is, we should do better, right? There is nothing special about two-way fixed effects, right? In terms to highlight treatment effect dynamics, right? We can do much better if we split the analysis into 3 steps: identification, aggregation, and estimation and inference, right? And once we do this, you're gonna have multiple options to construct something that is meaningful for you, right? And Callaway and Sant'Anna provides one of these procedures that helps you to respect your assumptions, and actually the estimation procedure, your estimator is gonna be actually doing what you think it is doing it, right? So again, all tools available for easy implementation. And if you guys have any questions, I'm here to answer. You can follow up by email, on Twitter as well. I'm very happy to engage in these communications. Thank you very much.
Perfect. Thanks so much, Pedro, for walking us through this approach. Yeah, very much looking forward to the discussion. To the audience, please submit your questions through the chat. And I would actually like to ask Rodrigo Oliveira, who's also a research associate at UNU-WIDER, to kick off our discussion, because I know he has been closely following your work and was already so very excited about this talk. So Rodrigo, if you want to go ahead with your question, and then the audience can continue submitting questions to the chat. Thanks.
Hi, thank you, Simone. Can you hear me?
Yes, perfect.
Hi, Pedro. Nice to see you again. Now in English. Last time was in Portuguese. So, Pedro, I have first, thank you for your brilliant presentation. It was amazing to watch again. I have some questions. It's basically to motivate the debate, and of course, doubts that I have when I read the paper and I see some applications. The first one is, and also thinking about problems that I usually solve in research, mainly using Brazilian data. For example, the first question is, what if we don't have good covariates? And the second question that I have is kind of, I don't know if someone asked you that, but my question is, when I don't need Callaway and Sant'Anna, when can I use, for example, two-way fixed effects, or I don't need to care about what the innovation you are doing in the paper. Yeah, I think I can start with this two questions. Thank you.
No, these are perfect. These are perfect. Thank you very much, Rodrigo. Great talking to you again. And this is like the first question about covariates, right? So what happens, when do you need covariates? I'm going to answer like, when do you need covariates to make this analysis more credible, right? So here I want to stress what we have is time invariant covariates, right? So covariates do not move over time. And this is a big pet peeve of mine because time varying covariates are very complicated to handle in different setups in my personal view. Why is that? Many times we add covariates in the procedure, and these covariates are measured in periods after treatment had already started. And there is a good chance these covariates are correlated with unobserved factors that affect the outcome and the treatment decision. So this acts like kind of a collider bias. So including post-treatment covariates into the analysis, it is kind of like as dangerous as you can think of. I mean, as two-way fixed effects in the beginning. So I don't like time varying covariates so much. So that's why we kind of reframe the analysis to handle time invariant covariates. So, and when do you want, I mean, that's first note. In that case, do we still need covariates? Indifference and difference covariates is all about allowing for covariate specific trends, right? So do you want to allow that the evolution of the outcome, right, is different across different covariate values, right? So I don't know, in the US, the minimum wage in the Northeast, right, would have involved, does employment in the Northeast of the US would evolve in a similar manner as the employment in the South of the US in the absence of increase of minimum wage, right? If you believe that like, no, I have to allow for region specific trends, covariates comes into the game, right? But in some situations, covariates are not required, right? So in those cases, you don't have to play around with this double robust, like inverse probability weighting or regression adjustment procedures. You can do canonical DID, and this is where things shine. Second question, so this is my view, right? So second question, when you do not need Caloyan-Sant'Anna. There are many situations you don't need it. So this is gonna mean, so let's put it this way. There are two answers here. The one answer is like when a priori you don't need it, and when a posteriori it doesn't change there is no meaningful difference between two-way fixed effects and Caloyan-Sant'Anna. A priori, like let me first focus on the a priori question. So a priori, you don't need Caloyan-Sant'Anna if treatment does not vary over time. Treatment adoption does not vary over time. So everybody's treated in a given date. So I have multiple time periods, right? But everybody's treated in the same date. In those cases, I don't need, there is no problem with Caloyan-Sant'Anna, like, or with two-way fixed effects. Everything's gonna be good to go, right? So I have a never treated unit, I have a set of treated units, but the treatment date is fixed. So two-way fixed effects works very well. Without covariates, with covariates, the game is different. Without covariates, this works well. Now, when two-way fixed effects gonna give very different answers from Caloyan-Sant'Anna, right? So the answer is gonna be very different whenever you have a lot of treatment effect dynamics. So dynamics play a big role. So if treatment effects evolve over time, right? And furthermore, all units are eventually treated. This is gonna be when the difference is gonna be magnified. If, I mean, you have a very large never treated group, right? Caloyan-Sant'Anna and two-way fixed effects gonna give similar parameters, right? Without covariates. So this is gonna be similar. On the other hand, it's not really, I mean, from my personal view, I'm kind of a control freak, right? I like having control of all the weights. I like to be in charge, right? In that sense, I don't like two-way fixed effects too much because we are letting our estimation method choose the aggregation scheme that we care. What I like to do is like, well, I care, I mean, nobody tells me what I care, right? So I want to decide by myself. So that's the beauty of Caloyan-Sant'Anna in my personal view, because I mean, we can construct things that we care that does not depend on estimation procedures. So that's more or less long answer to your questions.
Thank you.
Great. Thanks so much, Pedro. I'm going to summarize some of the questions from the chat and then also allow some people to ask questions. So on the technical side, we had two questions regarding whether you always need to have a balanced panel of your treated units and be able to follow all of them over time. And if so, or if not, and to what extent it's a problem if you don't.
Yeah, so we don't require, actually in our software, we allow for unbalanced panel. We even allow for repeated cross-section case, which is the most extreme like version of unbalanced panel, because we observe only one, in each point in time, we only observe one unit, so there's no repetition in this panel. So we can allow for that, right? So we can allow for unbalanced panel or repeated cross-section case. In these situations, in the software, in the DID package, you have, the way you can do that, there is an option called allow unbalanced panel. You can set it to true. Then you're not gonna drop, you're not gonna force balance. Right, so that's the thing. The complication of these setups is that once you have an unbalanced panel, you have to think about potential problems with compositional changes over time, right? In our paper, we assume that you have some kind of stationarity assumption that somehow rule out compositional changes over time, but this is something that is different from the panel data.
And your approach basically means that when you always need to have a non-treated cohort, right? So if all cohorts are eventually treated, you would need to drop the last period.
Yes, so that's exactly the way we do. So if everybody's eventually treated, like we cannot identify treatment effects in those time periods where all units are treated. So what we're gonna do is like until the period before the last cohort is actually treated, we can identify the ATTGTs. But once the last cohort is treated, it's game over. There is no valid comparison group, right? So we cannot push it forward with differences without extra assumptions.
I see Josh Butlander in the audience who also had a question. Maybe if you like, Josh, you could unmute and ask it live.
Okay, thanks. Actually, I don't. It's just really. I think this is a great paper, and I love the package. Also, I think the paper is very clearly written, so thank you for that. But a paper I haven't read, so I was being a bit cheeky and asking about it. Is this new event study paper by Kirill Borisiak and Yaraval and Spies. And I need to get to that, but I was wondering what your views are as to how that paper differs from yours and what its strengths and weaknesses are relative to your paper.
No, that's a great question. I mean, so that paper is somehow like they have been around for a long time, right? So Kirill and Xavier has this version back into 2016 or 2017, and that was like one of the earliest versions of pointing out all these problems with two-way fixed effects, right? So that's for background. That paper and a version of the Chaise-Martin and Dauto-Follier as well, they're like the very early papers pointing out problems with two-way fixed effects. So from the stats point of view, they are like the pioneers. So they are pioneers of the problems. So that's, I think, is important to give credit to them as much as we can because it's all there. Now, the new version have this estimation procedure that is slightly different than what we have here, right? So Kirill gonna disagree with me from the way I say. I talk to Kirill a lot on these things. So they have different ways. They are willing to exploit parallel pre-treatment trends as well, right? So I mean, Callaway and Sant'Anna, we don't exploit parallel pre-treatment trends, right? Because we think, well, we're gonna try to make minimal assumptions. So we're gonna use only the time periods before treatment takes place as the baseline period. So this new paper by Kirill, Xavier, and Jan, they are willing to exploit all the lags, all the past as well. And that in general gonna improve efficiency, right? So if you have zero pre-trends and you're willing to exploit that, right, you're gonna get efficiency gains compared to what we have here. There's some other that's what they show. There's also like some other smaller differences in terms of the underlying assumptions, right? They are kind of like they are allow for different types of parallel trends. Outside their setup is slightly different than parallel trends. They have some kind of like factor model or like interactive fixed effects procedure, right? But the factors are observed. That is different than parallel trends. So to summarize the answer, like what they are the early, so they have to have credit for that no matter what, and they're willing to use additional structure that can improve efficiency compared to what we do.
Right, makes sense. I think this connects to another question that I think several people asked in the chat about how many leads or lags do you need for your approach? And I think I understood you don't go long back in time to establish this parallel trends assumption, because there are a few people saying, okay, only have one period, only have 2 periods, etc. So it would still work with your approach.
So that's a great question, because I mean, I haven't stressed this at all in the paper. In the paper, it's stressed in the presentation. So this depends a lot on the comparison group you're using it. If you're using the never treated group, we do not restrict at all pre-trends. So pre-trend, before treatment takes place, I have here in red. So you're making parallel trends only about the future, right? So you can allow for unparalleled pre-trends for identification, right? You may say, well, I don't want to allow for that, because if I have unparalleled pre-trends, why should I believe in parallel post-trends? I say, well, that's not my business. My business is to formalize what you need and what you don't need, right? So here is like, you don't need parallel pre-trends if you use never treated as a comparison group. Now, the situation is different when you use the not yet treated as a comparison group, because not yet treated does impose some versions of parallel pre-trends, not for all the way back in period, but there is some, like this in red part here, that is kind of hidden, some parallel pre-trends in position. So this is like more complicated. So there is a trade-off on how stronger are my assumptions, like, and how big are my comparison group. So bigger comparison groups, in the sense that I want to use more units, not yet treated units. Well, I'm going to rely on stronger assumptions, at least in the technical side, right? If I want to use the never treated group, I don't have to restrict pre-treatment periods. Now, this is a technical discussion, right? So which one should you go? It's very application dependent, right? So if you, in your application, like you believe that like, well, 2 or 3 pre-trends does not matter, well, go ahead, use it. We are not really exploiting it, these additional restrictions in the estimation procedure, but I mean, it's kind of like there. Oh yeah, and just to also like leads and lags, right? So what do we have here as leads and lags in this specification here? We're not going to rely on this kind of behavior in Callaway and Sant'Anna, right? So we're not going to have a regression that is similar to this. So at the end of the day, it's your choice of how many event times you want to display, right? So what ATTGT is going to do, they're going to compute all possible event times that you can actually come up with. And then say, I don't care about all of them. I only care about a given window. Well, then you can set up the minimum E and the maximum E to display in your application. And our confidence intervals going to be adjusted for that choice that you have.
Right, makes a lot of sense. And I think the beauty is that it makes those assumptions very transparent. That is really nice about it. So we are kind of close to the end. Maybe I'm going to pose a final question that probably you have been asked a lot, which is kind of about what difference does it make in the applications you have seen? Like what's the size of the bias, what's the direction of the bias, and how much should people worry who have probably run this type of policy evaluation using 2-way fixed effects? What's your final stake on this if you want to wrap it with this?
This is I mean, I think like it's hard to, I mean, again, like it's hard to a priori tell if this is going to matter or not, right? Because this is very application dependent, right? And I mean, I think it's like, this is kind of like goes against the way I think about methods, because I think like, well, if I know that 2-way fixed effects gonna get things right if conditions A, B, C, D, E, F, G are satisfied, right? And I know there is an alternative method that does not rely on these additional conditions. Why should I be obsessed with the 2-way fixed effects method, right? So I think it's like, if I have an alternative that is more robust and there is no meaningful like difference in terms of how easy it is to implement, right? So I would say, well, I'm not going to favor 2A fixed effects from the a priori point of view. Now, when does it really matter, right? I mean, in our application for minimum wage, it's a case that it does matter, right? So when you do 2A fixed effects, you get essentially there is no effect, no raising minimum wage, there is no effect on teen employment. But once you do what we propose in the paper with ATTGT, right? No matter how you aggregate these ATTGTs, you find a negative effect, right? So there is a disemployment effect. So when you see this, which one do you believe? I say, well, I know in controlled experiments, in simulated exercise, all sorts of bias baked into 2A fixed effects, right? And I know that our procedure does not suffer from those bias when we have treatment effect heterogeneity. So from my point of view, causal inference is all about heterogeneity. It's like we are embracing heterogeneity. 2A fixed effect is going the opposite direction. We are ruling out heterogeneity. So, I mean, from that perspective, even when they are similar, I would say, well, yeah, fine, they are similar. That's good for 2A fixed effects. But I mean, still, I would not favor it because, again, I'm a control freak. I like controlling everything.
Perfect. Thank you so much. I think we're even slightly over time, but yeah, I certainly learned a lot, and I think many people in our audience really appreciates this presentation. Thanks so much. And yeah, I look forward to seeing more papers maybe using this approach. And as you said, it's all available. And yeah, looking forward to further engagements. Thank you.
Thank you, everybody. Really had a lot of fun. And again, if I didn't manage to answer your questions, please feel free to write me. And I mean, I'm going to try to follow up with that as long as I have available time. Thanks.
Thank you.